Hello and welcome back. And so now we want to start to measure properties of planets that are in our galaxy, that are outside the solar system. So we're going to call these extrasolar planets. And the first property that we want to measure is how long is it going to take this planet to orbit its star. And the way that we're going to do this is by measuring the brightness of that star. So we're going to attach our photometer, that was the device that measures the brightness of objects, to our telescope. We're going to train it on a particular star, and then we're going to watch that star over the course of many, many nights, possibly many, many years. So it's going to take a long time in order to gather this information. And then what we're going to do is we're going to make a graph of the brightness. So the brightness of that star versus time. So we go out, let's say we go out tonight, we look at that star, and our photometer says it has a certain brightness. Okay, then we go out the next night, we look at the same star, it has a certain brightness, and so you can see that this might take many, many days, many, many years for this to collect enough data. But eventually the brightness of that star is going to start to dim, and then it's going to get bright again, and then it's going to go back to normal, and then after a certain period of time has gone by, it's going to start to get dim again, and then it's going to get bright again, and then it's going to continue at that brightness. So what we're going to do then is measure the distance from here over to here, and the amount of time that elapses is going to be the amount of time that it took a planet to go around its star. Because let's say that the planet is over here, it hasn't gotten to its star yet, so the brightness hasn't changed. But as the planet gets in front of the star, now all of a sudden the brightness of the star is going to dim because there's something in front of it. And so when the planet gets over to here, okay, now it's on the other side of the star, and so the brightness of the star increased. So all we need to look for is a dip and then another dip, and then we measure the amount of time it took to go from here to here, and then that would be the amount of time it took the planet to go around its star. But there's a problem with this. What about if there had been two planets that are in orbit around that star? Then what's going to happen? Well, then for each of the planets, it's going to have its own dip, and it might be kind of difficult to tell which dips go with which planet. Well, one way of figuring it out is by looking at the how often is it dipping. And so if you've got, let's say that you have another dip in addition to these dips over here, well, it's not going to occur in the same amount of time it took to go from here to here. So that would be one way of telling the difference. Another way of telling the difference would be how much does it dim the star. So the bigger the planet is, the more it's going to cause the light to dip. And so by measuring the dips in the brightness of the star, you can also tell the difference between the various planets that are in orbit around it. Pretty difficult, but it can be done. Okay, now let's try a second way of figuring out the period. And so this is going to be by looking at the spectrum of the light given off by the star. So we had another device that we could put on our telescope called the diffraction grating. And so the diffraction grating was a piece of plastic that had a whole bunch of lines scratched into it. And then as the light from the star went through that piece of plastic, it would be diffracted, it would open up, And so you would see the rainbow of colors being produced by that particular star. And so in the left-hand side, you see the absorption spectrum of the light given off by the parent star. Okay, now, if you've got a star and then you've got a planet, you're accustomed to thinking that this planet will go around the star. But it's not that simple, because in actuality, both the star and the planet are in orbit around their center of mass. So we talked about center of mass. So again, think about a teeter-totter. So when you've got a teeter-totter, the pivot point is going to be the where the center of mass is going to be located at. So imagine that you've got a very heavy object over here and you want to balance it with the very light object, then you need to put the very light object out here. So do you see that the distance from here to here is different than the distance from here to here? And so imagine that you've got a big star and you got a little planet over there. So what would happen is that they're in orbit around each other, and they're in orbit around this pivot point, which is going to be the center of mass. So that means that when we take our telescope and we look at this star, the star is going to be wobbling very, very slightly, but it's going to be wobbling because imagine now this teeter-totter can rotate. So as it's rotating, can you see that this object sometimes would be over here and sometimes it would be over here, and it would be wobbling back and forth. So we can look at that wobbling by using the Doppler effect. Okay, so now what was the Doppler effect? So the Doppler effect was that when the source of light or a source of a sound is moving towards you, its frequency will go up. And then as it goes away from you, its frequency will go down. So you should remember that again from unit number 1. Think about a car horn. So as the car is coming towards you, it's honking its horn, and the frequency of that sound goes up as it approaches you, and then as it goes away from you, the frequency goes down. So light will do the same thing. So if the source of the light from the star is moving towards us, its frequency is going to go up. So because this star is wobbling, it's sometimes the star is moving towards you, and then sometimes the star is going away from you because it's going around in a circle. So we can measure this Doppler shift in its spectrum. So if you look at that left-hand picture, the bottom picture shows you the ordinary spectrum, and then it shows you what would that spectrum look like if the star was coming towards you, and what would the spectrum look like if the star is moving away from you. So then what we do is we plot it again on a piece of paper. So we're going to plot the amount of shift in the wavelength, so that would be going up and down, versus time going sideways. And then we look once again for when does it repeat itself, and then that is going to be the period of the planet going around its star. Again, pretty complicated, but it's pretty cool that we can be looking at a planet that could be millions of miles, millions of kilometers away from the Earth, and yet we'll be able to figure out how long is it taking that planet to go around its star. All right, the next thing that we're going to do is we're going to figure out the radius of the orbit of that planet, and we're going to do that in the next segment.